Hi everyone, my name is Naman and I'm joined by my teammates Anubhav, Jihun, and Junseong. And our work is on mitigating hallucination in large vision language models. So, coming to the problem description, our main goal is to reduce hallucinations by using attention based image patch adjustments at inference time. The relevance of this problem comes in safety critical applications where visual misinterpretations can cause serious failures. And in terms of the background, we treat the paper which introduces visual contrastic decoding as a baseline, and building on top of their IDR method adjusts image brightness based on the attention maps that we extract. And we use this to tune the logics to reduce the hallucinations, and we outperform the baseline in terms of both the accuracy and the FN score. So for the task, we focus on using attention maps to observe the image level brightness, and overall we tune the logics after inference time to reduce the hallucinations. In the first step, we extract the attention maps from the images. Then we use the margin and highlight images to identify relevant and irrelevant patches in the image. Then we do a selective patch adjustment where we amplify the relevant patches and suppress the irrelevant patches, after which we generate the refined outputs and evaluate our results on the evaluation dataset.
Mhm. So here is an overview of the test scan method. We use a dataset of 600 instances sampled from MS COCO. Each instance consists of an image paired with a caption that includes a list of ground truth objects mapped to the image. For evaluation, we use the POP metric, and POP queries whether each ground truth object mentioned in the caption actually exists in the image. For example, if the object surfboard appears in the image, then POP asks a binary question about whether it is present or not in the image. Accordingly, the evaluation metrics includes accuracy, precision, F1 scores, and others. And in the next slide, in the attention map integration step, we identify image patches where the attention scores are highly concentrated by selecting the top 10% of attention maps based on variance score. These selected maps are then aggregated using Gaussian blurring. The resulting integrated attention map provides spatial information that highlights the most important objects in the image. Using this location information, we generate edited versions of the image, and one that emphasizes the key objects and another that occludes them. Each edited image respectively decreases or increases hallucinations in the model predictions.
In graded decoding can hallucinate because it does not sufficiently verify visual grounding. Our method uses attention to create a highlight image that retains important patches and a margin image that contains less relevant ones. By amplifying the signal from the highlight and reducing the influence of the margin, we can steer the logic toward what is actually present in the image, allowing the model to correctly identify the bicycle rather than hallucinating an object like shopping cart. We evaluate our approach using level 1.57b on the POP benchmark. We report accuracy, precision, and F1 score across the random, popular, and adversarial split. We also vary two coefficient, alpha, which suppresses signal from less relevant region, and beta, which amplifies signal from important regions.
So coming to the results, we evaluated our proposed method using different hyperparameters of alpha and beta, which control the suppression and amplification of the irrelevant and relevant patches. So the key takeaway is that one thing we can see from the graph is that hallucination can indeed be steered at inference because we can see the accuracy going up and down. Alpha should we can also notice from the graph that alpha should be kept small, which means that the irrelevant patches should not be suppressed too much. It can harm the performance. But the overall goal is that the overall finding is that the model responds more positively to when we boost the actual relevant regions instead of suppressing the irrelevant regions. So the best performance was achieved for us in our testing was with extremely low suppression of irrelevant patches, but with medium amplification of the relevant patches, which again solidifies our grounding. So just to conclude, so our proposed method does indeed reduce hallucinations, and we had some performance improvements across all the benchmarks that we had. The main thing is that this method does not require any retraining, that makes it pretty lightweight, and it's also interpretable, as we saw. Which makes it extremely relevant for real-world applications because it's interpretable, and again, it does not require any retraining. For some future works, if we had enough time, we would have focused more like testing it across like multiple families of VLMs to make sure that these findings are generalizable across like different benchmarks and different types of VLMs. So here are the references if anyone needs to read more on the above. Thank you.